they synthesized. And they did the confirmation by doing a nosy, and they've labeled all of these peaks. If we draw out, well, I can start with this one. If we look at this one, and we have these hydrogens on the same side, the interaction from, so this is 13, 14, 15, and 16. The interaction between 13 and 14 and 13 and 15 should be strong, because they're close in space, so their NOE should be strong. And the interaction between 16 and 13 should be weak. And let's see, any others? The interaction between the 17 here, so we have hydrogens out here. If they rotate, there may be an interaction here that would be a little bit stronger. And then on the one they have on here, the confirmation they have on here, this interaction between 13 and 14 would be relatively weak. And this one's going to be relatively weak. And the hydrogen at 15 to 17 should be relatively weak as well. They're showing that one. That's it. And then you could also look at the other stereo center over there with the alkyl chain. What they did see was a strong correlation between 16 and 14 and 15. Oh, that was the other one. So this correlation here would be weak between those two hydrogens if it was this conformation. So they saw 14 and 15 and 16 to have very strong NOEs, and the 13 to 14, 15 to have a weaker NOE. And so this supported their conclusion that they got the structure on the board there rather than, or on the screen rather than on the board. Graham?
Maybe I just misheard you, but you said that 13 to 17 would be pretty weak. That looks really strong.
So this is our 13 to 17. Well, no, we can see it here if that could be strong, and it would be strong here as well. Well, no, it would be weaker here, wouldn't it? So if we went 13 to 17 over here, we're going to see a weak interaction. On this one, because that hydrogen is down under the ring and the alkyl group's pointing towards it, then that's going to be a stronger interaction than it would be over here. Okay. So that's what the NOE can tell you. And like I said, it's going to be an advanced technique that you wouldn't do until you pretty much know the structure. And you would want to compare the COSY because you are going to see a weak interaction between 13 and 14 and 15 just because we know they're coupled. And so they are going to show up in here. Correct?
So you want to either do the top or the bottom just like in COSY?
Yes, so the diagonal is the same thing. You would see the same analysis and the same peaks
Those
down
are like
here.
dots coming up from the diagonal. Do you count those?
This is going to be what looks like to me a little bit of noise. When it's surrounding the one peak, you get a little bit of extra signal as it goes farther away. The nosy interaction is a rather weak interaction, and it needs a lot of scans, or you have to bump up you get a lot of noise. And so in this case, they may have a little bit of noise here that is interrupting that signal. This is actually a phase-sensitive nosy. And in this case, the blue is a negative peak, so that's one that you would ignore. And the red are the ones that we want to focus on. So it would depend on whether you did an absolute value or a phase-sensitive one. I don't want to get into that too much. Overall, if you get a nosy, you're looking for the interaction. And so what I would expect on an exam or something would be that you would be able to identify by looking at a molecule in a certain conformation whether they would have a strong NOE or a weak NOE, and then being able to say if these two have a strong NOE, how does that relate to two different conformations or something like that. So you could know that relationship.
So
Brennan?
just to be clear then, we won't need to actually analyze a nosy on a test then, we'll just need to be able to talk about it.
Right. I don't think I have time to take a nosy. I was trying to run one on some of my samples when there was at least an hour and a half on the NMR. It's a little challenging. And that's maybe giving me an okay result. They weren't giving me very good. So. No, they're harder. And so just if you understand the concept, you'll have enough time spent on all the other spectra. Speaking of which, let's look at the next molecule here. So everything we're going to talk about from now on is going to be on this molecule. I'm going to label these so that we are consistent. Let's do A, B, C, D, E, F, G for the hydrogen groups that are on this molecule. In looking at the NMR here, this is our proton NMR, there's a few peaks that we can pick out pretty simply to identify what they are based on their chemical shift and their splitting. Then a few others that we're going to have to look in a little bit more depth in order to determine whether they're which one they are out of a couple of these. So the first one that's easy to identify is A. It happens to be this tall peak here, which is integrating to 5.7 because it just so happens to overlap with another signal under here. And so there's 3 for the methyl group, and then there's a little bit another signal here, and that's something else in the molecule. The other easiest one is our end of the chain G, because it's a nice triplet, and we know that it has 2 neighbors, so that would split that into a triplet. We know, based on chemical shift of 5 to 6, that these 2 are alkene. At this point, we may not know which is which.
I guess I'm just unsure why A was easy to assign.
Because A is a methyl group, so it's that doesn't have any neighbors, so it's the only singlet in the structure. And yeah, it's hard to see because it's overlapping with the other. But when I zoom in on that, you see that it's a singlet there.
Okay.
So we know that this is C and D, but we're not 100% sure which is which. If I was going just based on the structure, the C is a little closer to the alcohol, or not the alcohol, the oxygen of the ester, so that may be up here, but I'm not going to assign that one yet. The other one is this peak between 4 and 5. Hydrogens that are on carbons next to an oxygen are going to be strongly deshielded, more so than anything else in the molecule here, so that's going to be B, and it integrates to 2. Now E and F, we can probably tentatively assign F as the one that's second furthest upfield because it's going to be furthest away from anything. And then E is going to be slightly downfield because it's alpha to an alkene. So all of those approximate chemical shift ranges you need to know for the test. The calculations with the big old tables and stuff like that, I would provide for you for the test. So you need to know that a general range of each of the different types of functional groups for carbon and proton, but I'll give you the calculations for any calculations you need to do.
What kind of calculations?
Like the chemical shift of a carbon or a proton based on what the substituents are around it. Yeah, I think the last homework set. So we know that these are either C or D. At this point, we probably want to look at the COSY to help identify which one is which. We're going to flip to 2 slides later is the COSY where we have the proton versus proton. And we're going to look at the cross peaks, ignoring ignoring the diagonal. Let's start with the most upfield signals. So on your right, up right there, we have the CH3 group. You know what? Before I even get too much further, we need to assign what we know so far, because otherwise it's harder to keep straight. Let's do that. So this would be my first step if I was labeling a cozy, was to label what I know in terms of the structure. And I'll relabel the structure here so we can refer to it without changing the slide. And from the cozy we see that G and F right here are coupling each other, so I'll just label that as the FG coupling peak, and then we have another one of those on the other side of the diagonal, but we'll just ignore that right now. And then if we look at F going across here, so starting from there and going across, we see another peak for our cozy, meaning that E and F are coupling each other. And then we don't have anything else with interaction between E and F and G, so we'll move on to the peak here for B. So we see E to B interacting. This is a weak interaction though. So if we look at the structure here, that would be a J5 coupling. And that's a homoallylic coupling. So they're on either side of the alkene. One's allylic to one side of the alkene, one's allylic to the other side. And those can potentially couple. And we see a very slight coupling there on this example. And then E is also coupling with our peak at about 5.7. So that peak is the only one of the alkenes that's coupling with E. And if we look at our structure there, E to D should have a strong coupling, and that should be stronger than C. So this actually tells us that this peak here is D, even though just kind of looking at the structure we thought it might have been C.
Why would that
Yeah,
be?
why
Isn't
would
that
that be
stronger?
We could probably do a calculation on it. There's other steric effects and things that affect those chemical shifts, and so I don't know quite why it is, but we could probably do a calculation to figure that out.
I just feel like to me, like it's like obvious that C would be the most central. Like if I was just gonna assign.
Right, and that's why you gotta be careful sometimes with that. The general ranges will tell you approximately which one is which, but sometimes they're not as obvious as you think. And from the cozy, we can see that they're coupling, and we'll see that in the coupling constants as well. And that leaves us, so this was the E to D coupling. Then we'll come down to the last section down here. We have a slight coupling between B and D, and that's weaker because that's a J4 coupling, and a stronger coupling between C and B. That's a 1-bond coupling, or sorry, a 3-bond coupling. And then our D to C coupling is shown here in the last peak on the cozy there.
If there's B to D coupling, why wouldn't there be E to C coupling?
There actually is.
You just, okay.
And if I brought this up and we looked further into the deeper to the weaker signals, we probably would see that. And we actually do see it in the splitting pattern, but we don't see it here. It is a weak, and you can see that these are just barely showing up, so maybe I needed just a little bit more signal there. So Cozy helped us to then assign the last peaks, and we know which coupling constants we're going to need to measure in order to do a full tree diagram. So we know we need a JCD, we need a JCB, we need a JED, we need a JED, we need a JEB, JEF, and I'm just taking those cross peaks and writing them down. And JFG, and then that last one, that I'll put a question mark on, the J, what were we saying, the B to D? Is that the one?
The C to E.
C to E?
Is not.
Yeah, we have B to D, but not C to E. So we'll put a question mark on that one. And that maybe that it's actually a smaller coupling, so it doesn't show up as easily here. So those are all the ones we're going to have to measure. Okay, I'll go through one example. But you guys are getting pretty good at measuring those. Keep going. I'm sure the comfort box is fine. So here's our first peak, the triplet, which when I went to measure the coupling constants, they aren't equivalent on either side of this triplet, even though it should be. What I did find though is that if I add them up and I divide by 2, it matches something else in the polynomial. So this is our peak at 0.8. And between those two, if you add them up, you get 14.66. And if you divide that by 2, you get 7.33. And if I pull up the next peak over, the 7.33 is the coupling of the peak for F, this sextet looking thing. Yeah.
I'm sorry, is the adding and then the dividing by 2 something intuitive that we should go into?
No, that was in a really simple triplet, probably, maybe. Unless it's split into a triplet by 2 different things that are very similar. So if it had you have a CH2 that are diastereotopic, and one splitting 7.1, one splitting 7.5, you should be able to find that elsewhere in the molecule. I didn't. And I knew there was a 7.33 on this one. So not entirely no. But on a simple structure like that, you could get away with that. In a more complex multiplet, I'm going to say I wouldn't want to do that.
Also, kind of looked like the measurement tool was a little left of the peak.
Yeah, and the peaks are broadened a little bit by these long-range couplings, and so with real spectrum, it's a problem. If we simulated everything, we'd be okay, right? So our coupling between F and G is 7.33 hertz. And then we have E to F as our next one over. So this is F, and it does get split into a sextet. E to F is actually slightly different than that. So E mentioned, there's that singlet that goes up through the middle of it, but it has a 7.79 over here, and so I think that's the coupling constant between E and F. And 7.79 and 7.33 are close enough that when you start doing the tree diagram, they're going to be overlapping, and you get what it looks like a sextet, but it's not quite a sextet. It's more like a triplet of quartets, because it's got 2 on one side and 3 on the other. So the quartets split into a triplet, but they just happen to be overlapping, so we'll call it a sextet.
So the F peak had a 7.33.
The F peak has the 7.33, and if you look at these peaks, they're not very pretty. These are kind of chopped off because they're lopsided. And let's see, they don't add up to exactly 7.33 plus 7.33.
So then how do you know that like that's not the coupling constant for EG? Like, well, since they're all 7 points.
E and G are not coupling each other
At all.
because of the cozy. We can see that.
So if it's not coupled on the cozy, we're not going to have a J coupling peak on here.
Unless it's like a 1 or, yeah, it wouldn't be anything strong like that. Then we get to a doublet 4.5, and we have a coupling constant, 2 coupling constants for this one. So this is B has 0.92 and 6.41 for its coupling constants. If you look at it though, we do see these peaks not going straight up, so there's a little bit of some other fuzziness that's happening there, and I think that's the longer range with B to D coupling that we don't see, but it's a very weak coupling. We'll see it a little bit messier in the D peak. So B has those coupling constant values, then we have C, is this 5.5 is C. C has some messiness to it, a little bit. We see a 1.37, which I'm not sure what that's from. 6.41, 12.82. Although if you take 12.82 and you divide it by 2, it equals 6.41. And that's actually, that makes sense because there's 2 protons on B, and so each of them is going to split it by 6.41. And we see this as a triplet here, and that makes sense. And then the other coupling constant is the 14.20. And I'm just going to list out the rest of them here, and then we'll come back and assign all of those. That's what I did when I was assigning these. So D has a 6.87, a 0.92, which I don't have shown there, but it's this peak to this peak is a 0.92. That's the only one that I could get a nice signal from, or maybe it was these 2. You can see there is a splitting there, but we can't quite measure it because the peak's not distinguishing itself on the NMR. But there is a 0.92 and a 14.20 on there, and then the 15.11, but that's actually just a, if you add these 2 together, you're going to get that, so we're going to ignore that one, and we're going to ignore that one because they're either additive of 2 J coupling values or multiples, and we can ignore those. So now,
when you go to draw them in the tree diagram, you have to do 6.87 twice, right?
yes, you'd have to do a doublet 6.87, doublet again 6.87. And so here we see the 14.2 is going to be our CD,
I'm sorry, why did you say
It's written up there, and I think it's DDE.
Or did you mean 6.41?
6.41. Wait, what? What was my question? Okay, say it again.
Why would we double 6.87 if that is in fact the one that is multiple?
I doubled this one, the 6.4, or is it, this one's a multiplet of that too. We have, if you look at the structure, there's
No,
two
it's not.
hydrogens at B
Close.
and two hydrogens at E.
No, it's not that close to me.
And so each of those is going to split their neighbors once, which adds up to twice. So you're going to see a triplet-like structure. And so that's where
6.92 equals
like,
92.
the
Yeah, but where does
clearer on the other one.
What?
Where does 6.87 come
Is
in?
it up there on the thing?
Yes.
On
it's
this
gonna
one,
be the E to D.
you see the triplet-like structure. That's because they have two hydrogens. They're splitting them into a triplet. And then we have other messiness splitting it into another doublet and another triplet.
Why is 6.87 times 2 equal 15.11? Why did we cross that off?
We've got two hydrogens that are splitting it, right?
The D?
From E. This is actually the E to D value. And that's going to split it twice, so if we have a doubled value, it's just 6.87 once and 6.87 twice, and that gives you the 15.
Didn't you
I'm just
say
like,
that
why
was
But 6.87 times 2 isn't
Is it
15.1.
13?
Yeah.
Yeah.
The match?
You said it was the 0.92 plus the 14.2.
Is it that? Is it?
That
Yeah.
equals 15.1.
That makes sense.
Yeah, that was what I.
Yeah. Sorry. That one is because we added two together and came up with that value. So then we're looking at like here to the wrong one, right? We're looking at the wrong set of peaks on that NMR. Did I get?
Or would be 16. Oh, no, sorry.
Okay, okay. So lining these all up, we've got this is our B to C. 6.41, and then we have the B to D, 0.92. And our E to D is the 6.87. Yeah, I'm bringing it up here. This one's hard because this is a messy peak and it's overlapping, so it's hard to find that 6.87 in here. I think at one point I did find it, or I found a multiple of it. Which is
14 points.
Does that work? I can do math. Maybe.
No, it's not.
6.86.
It's 6.86 though, which is 6.87, so it's these two values added together. Right? So the 6 point, is that right? Is my math right?
Divided by
Not divided by 2, just subtract that up. Yeah. Okay.
More than that.
yeah, you're good.
But
Okay.
we would only, when we were drawing a tree diagram, we would only use 6.87 once, right? We would
So
only do
6.87
rows, so-
and a
It depends on
E
where's
to
the
B. Where did I get that one? Oh, it's really a less than 2. I'm not quite sure. It's one that just makes everything look messy, unfortunately.
If it's less than 2, that means
A weak coupling, so it could be like 0 or 1
you might not be
hertz.
able to find it then.
If you don't have sharp peaks on the top of everything, you're not going to find it very easily.
Yeah, so we're drawing 6.87 and 6.41 twice. So we're doing
So then
6.87 twice.
6.87, did I write it down here? No, just the E to D is the 6.87. So D has a 6.87, and then E had from here to here, well, here to here is 7.9, and then here to here is 6.87. Where they were lining up on those peaks. Kind of leaned on one side or the other to get that. Yeah.
And let's say your J value for EB.
I can't measure it. If I look at E and I look at B, I see there's like a little bit something more.
Yeah.
I'm not quite sure what it is.
Okay.
But I see there's coupling in the cozy.
Okay.
Okay. I want to do the depth and the carbon and the HSQC. That's actually pretty easy. We can do it pretty quickly. And then I'm going to draw some tree diagrams and I will post them on Blackboard. Okay, so first things first, so let's label this. And I'm going to keep the same letters here.
You missed a carbon.
I know, so I wanted to keep the same letters as the other ones. What comes after F or G, H? Okay. So carbon H is our carbonyl, and it's an ester, so it's going to show up around 170. That one's pretty easy to assign. The C and D are our alkenes, which show up between 100 and 150. They're both there, they're both CHs, so they both are negative and are depth 135, which is what this one is. So not so easy to assign at this point. We're going to hold on and look at the HSQC for those. HMQC, whichever one we're doing. And then the peak at 65 here. Yeah?
I'm sorry, unless I wrote it down wrong, I thought CH2 was in word on 135.
Yeah.
CH2's
Oh,
are.
did I face this backwards?
Yeah.
Oh, that makes a lot of sense.
I phased it backwards. I apologize.
Oh.
Either way, it looks like it's.
These are positive. These are negative. That's the challenge when you do that yourself, I guess. Yeah. Those are opposite. Everything's going to be completely opposite.
Awesome.
Our CH2 group then that's now negative going out is this B, which is next to the oxygen, will be de-shielded slightly. Then we have the other peaks here, G, F, E, and A. We can kind of tell that G and A are going to be the two that should be pointing up, that are pointing down. And the two that are pointing up should be B and E, but I'm not quite ready to assign those. It's going to be easier if we compare with the HSQC. Or if we didn't have that, if we did calculations. So very quickly, we have B, C, D, E, A, F, and G. These are the same assignments we did on the hydrogen, right? We can go through and then assign the signals on the carbon. So here, D corresponds with the more downfield peak.
Oh.
Can I use for erase marker on there? C is going to be our other alkene. We've already assigned this as H, B, and B work together. So this is our B carbon. This is why I kept the same letters, so it's a little easier to assign and explain. The A is this methyl group, which is really strong, and that is this one. Or G is the other CH3 group that was indicated by the depth, and then our E and F are shown here. So again, the C and the D are a little bit different than we may have just looking at it predicted, but that's something that you should have been able to see if you had a calculation table in front of you as well. So HSQC can help you identify things. Once you've identified the protons, it's really easy to identify all the carbons as well. And those peaks that are overlapping here, it's pretty easy to distinguish them now because they're in 2 dimensions and spread out.